Hello everyone, myself Uday Ranjan Goud, working as Assistant Professor in Department of Aeronautical Engineering, MLR Institute of Technology. So today we are going to have a session on shear flow in torsion, shear flow that is subjected to shear flow as well as torsion in fuselage. So hello everyone, myself Uday Ranjan Goud, working as Assistant Professor in Department of Aeronautical Engineering, MLR Institute of Technology. So in the previous session, we discussed about fuselage which are subjected to bending, and we solved a problem on it, how to calculate the direct stress distribution due to bending. Now in the present session, we are going to discuss the shear flow and torsion that when they are subjected to fuselage. So the fuselage when subjected to shear forces and the fuselage when subjected to torque. So how the shear flow distribution we are going to get, so that we will see in this module. So the learning outcomes in this module are students are able to analyze shear and torsion in fuselage and solve problems on shear flow distribution. So to understand that shear flow in fuselage cross sections, and let's straight away consider one problem related to shear. So the given fuselage section of example is subjected to a vertical shear load of 100 kilonewton that is applied at a distance of 150 mm from the vertical axis of symmetry. And for the idealized section shown in figure, calculate the distribution of shear flow in the section. Okay, so if you look at this problem, and previous diagram is also looking similar, and this diagram is also looking similar, but only thing here what we need to understand here, it is 100 kilonewton that is applied at a distance of 150 mm from the vertical axis of symmetry. So if this is a vertical axis of symmetry, and we know that the radius is 381 from here to here, so somewhere here, and the vertical shear load that is applied. So I am trying to draw here like this, and let's assume this is shear center. Okay, 100 kilonewton, not 150. 100 kilonewton is applied at a distance of 150 mm. So this distance you can consider it as 150 mm. Okay. So now the difference between the previous problem and this problem is nothing but, in the previous problem he has given the bending moment mx as 200 kilonewton meter that is applied, and he is asked to calculate the direct stress distribution. Okay. Now in the present analysis, he has given the vertical shear load of 100 kilonewton that is applied at a distance of 150 mm from the vertical axis of symmetry, and is asking to calculate the shear flow distribution. So one should understand the question clearly. Earlier, the previous problem which we solved in the previous session is nothing but it is a bending stress distribution problem in which the bending moments are given. Though the diagram looks similar, but the question is different and the application of load is different. So in the previous problem, the application of load is moment, and he asked to calculate the direct stress distribution. Whereas in this problem, the application of load is nothing but the shear load, that is a vertical shear load, and is asking to calculate the shear flow distribution. Okay. So here we have to follow the shear flow procedure. And then you can assume, consider Sx equal to 0, which is not given, and because of symmetry, the product of inertia also you can consider it as 0, and then the shear flow reduces to Qs equals to minus Sy by Ixx summation Br Yr. Okay, and it is a closed section, so you have to add Qs naught, additional constant shear flow, and that you can consider it as first equation. So clearly, by looking at this equation, Sy is the shear load that is given, and you need to calculate moment of inertia, and we calculated moment of inertia for the previous problem, and which is equals to 22.5 into 10 to the power of 6 mm power 4 that we got, because all the 16 stringers are similar and its thickness is also similar, and then the distance between each stringer is also different, is also same. So therefore we get the moment of inertia. The boom areas, the idealization also we have done in the previous problem, that is by considering for B1 and 2 panels, and then we calculated the boom areas. So approximate boom areas you got 216.6 for almost all the booms except 2 or 3 booms, and for which we got 216.7 Newton per mm square. So you can approximate and take the boom area as 216.6. Okay, and once you get the boom area, and you can calculate the shear flow distribution. So let's look into this problem. So first you have to calculate the moment of inertia. So as we already calculated moment of inertia in the previous session, I am not going to do again, and I am writing as it is, that is 22.5 into 10 to the power of 6. So when you try to substitute in the formula minus sy by ixx, so minus sy is 100 into 10 to the power of 3 and divided by 22.5 into 10 to the power of 6 is the moment of inertia, and then you get a constant, and then you'll rewrite that equation qs, and that you can consider it as equation number 2. Okay, so this is one we got, that is minus 100 into 10 to the power of 3 divided by that is not 22.5, it is 2.52 into 10 to the power of 6. Okay, so 2.52 into 10 to the power of 6. Okay, in fact 2.52 into 10 to the power of 8 we got, not 6. So 2.52 into 10 to the power of 8 we got for the previous one, and as before, so into summation r equals to 1 to infinity br yr plus qs naught. So this you can understand, and then when you try to reduce this calculation, you get minus 3.97 into 10 to the power of minus 4 summation r equals to 1 to n br yr plus qs naught. So this is very important. This is a fuselage cross section in which we are going to calculate the shear flow distribution of shear flow in the section. So but even though this is a fuselage section, and we see this like section as closed section, so that is why we have added a qs naught here. So the procedure for closed section, we know it very well that we need to make a cut somewhere in the section, and then we will have to make it open and calculate the rest of all the shear flows, and we write it as qb. Okay, and once all the shear flows are open section shear flows are found, then we add additional constant shear flow, that is qs naught, and then we'll take moment about a suitable point and we'll make equate to 0, so that you are going to calculate first qs naught, that additional constant shear flow that would have been exist in that panel. Okay, so once you get this qs naught value, and we'll superimpose onto the existing open section shear flows, so that you're going to get actual shear flows. So that is a regular procedure. Here we are going to proceed with that, and therefore you can see here in what we are doing here, it is the first term on the right hand side of equation 2 is the open section shear flow. That means from here to here we'll consider the open section shear flow qb. We therefore cut one of the skin panels. So let's say we are making a cut in panel 1-2 and calculate open section shear flow, that is qb. So the results are given which are presented in the table. Okay, so for example the panel 1-2. So here if we try to cut in panel 1-2, you are making a cut, and you can assume qb in that 1-2 that is equals to 0. Okay, or qs naught equal to we assume qb12 equal to 0 in this. So since this is open, now rest of the shear flows, rest of the section becomes open section. Since we made a cut here and we are assuming that the shear flow, that is the starting shear flow in 1-2 is 0. Okay, we are assuming. So the rest of the panels you can calculate the shear flows easily by the formula. So what is the formula we got? qs equals to minus 3.97 into 10 to the power of minus 4 summation r equals to 1 to n br yr plus qs naught we got. So once we make 1-2, then you can start finding rest of the shear flows. Okay, for example if you try to find out 2-3, okay, by looking at the diagram 2-3, I am writing here. So if you are calculating 2-3, how do you calculate? Minus 3.97 into 10 to the power of minus 4, looked for the boom area of 2 and its y distance. So boom area of 2 is 216.6, and its y distance from the centroid for boom to from here to here is nothing but 352, and we'll write here plus 352, and this is 0. Then this is 0 because starting shear flow we are assuming it as 0. Then you'll get q23. Okay, so that is what is taken here, q23, and you got minus 30.3. But we should not write this as q23, we have to write it as qb23. Okay, so we got minus 30.3 Newton per mm. And once you get this one, next we have to calculate qb34. So 34 minus 3.97 into 10 to the power of minus 4, 216.6 into and the distance is nothing but 269.5. the distance of boom 3 from the axis from here to here, which is nothing but 269.5. Okay, so that I am adding, but the starting shear flow for 3-4 would be 2-3. So therefore we have to add that result as QS0. Okay, so when you do that, you are going to get this as minus 53.5. Okay, so like that, this procedure will be extended till all the shear flows in all the panels are calculated up to 16.1. So 3-4 we calculated, next 4-5, 5-6, 6-7, 7-8 and so on. So therefore that will be given here, that is given here in the tabular column. Okay, so if you look at this one, and when you try to calculate for next 4-5, boom area is 216.6, you have to substitute 145.8 as the boom y distance, and you have to add minus 53.5, you are going to get 66. Next for 5-6, so 5 is unstressed, boom 5 is unstressed, so there is no y distance, so this you can consider as 0 y distance, but the same shear flow will be carried here also. And next, going on with 6-7, 6 boom area is 216.7 and its y distance is below the horizontal axis, so it is minus 145.8, then it's going to get minus 53.5, same as this one. Then again when you do the next one, then you are going to get 30.3, then you are going to get 0, then you are going to get the next one as minus 32.8 and so on. So these are all the open section shear flows what we got for all the 16 booms. So coming to all the 16 panels. Okay, so all these panels, first you have to calculate the shear flow distribution like this. So once you calculate the shear flow distribution for all the panels like this, remember what I said, that the next thing is you have, for example, this is the all the shear flows we got from 1 to 16, 2, 3, 4, 5 and 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So all these you got 16 booms. So this is the QB open section shear flow. Now all these shear flows are to be represented on this panel, shear fuselage. So all the shear flows you try to depict on this fuselage. For example, 1 to 2 we assume it as 0, and 2 to 3 we got minus 33.3, and 3 to 4 we got minus 53.5, and 4 to 5 we got minus 66. Like that you represent all the shear flows. Okay, plus what you need to do is you need to add additional constant shear flow, that is QS0 everywhere. Okay, why we are adding this? Because we are making a cut in the fuselage section at 1-2. If you don't make a cut, because it's a closed section obviously, so if you don't make a cut in panel 1-2, there would have been some shear flow, right? So we are trying to find out what is that shear flow that would have been existed and when the cut is not made. So that shear flow we are assuming it as QS0 as that additional constant shear flow that would have been existed, and then we should remember that again SY is acting from here 100 kN at a distance of 150 mm. That is also you have to remember, and then we'll try to apply moment about some suitable point to get the value of QS0. Once that QS0 is we have to superimpose all these. We have to superimpose QS0 in the clockwise direction what we considered onto this fuselage, superimpose, and then sometimes if both the directions of QS0 and this Q23, QB23, Q3, QB34 are same, they are going to add up, and if they are in the opposite direction, they are going to subtract. So therefore, that QS0 you have to add, or once you find QS0 by taking moment, you have to add to all these open section shear flows to get the actual shear flows. So that is the procedure. Okay, so let's look into that. So the QB shear flow distribution is symmetrical about CX axis, and the shear flow QS0 in the panel 1-2 is now found by taking the moments about a convenient moment about moment center C. So where he is taking moment? He is taking moment about this C, moment about the centroid. Okay, so when you take the moment about centroid, the left side we will try to write the moment due to shear. Left side we are going to write moment due to shear load. So shear load is 100 into 10 power 3, 100 kilonewton. This is SY equals to 100, and its perpendicular distance is 150. So in the left side we are going to write 100 into 150 shear load into perpendicular distance is going to get moment about this centroid C. So that is left side is because of the moment due to shear load SY. Right side we are going to write two things. Right side we are going to write moment due to shear flow, that is 1, plus moment due to constant shear flow. Moment due to open section shear flow, that is with the values what you got, you have to write the moment, plus next you have to write moment due to constant shear flow, that is QS naught. Okay, the two things you have to write on the right side. So that we will see. So 100 into 10 to the power of 3 into 150, and then to write the moment for the open section shear flows in the fuselage cross section, and we follow this, that is summation cyclic integral of QB into P into ds, where QB is the open section shear flow and P is nothing but the perpendicular distance and ds is nothing but the length that we will consider. Okay, so for example, QB is the shear flow, ds is the length, and which is the common length that we had got, that is nothing but 149.8. it's the circumference, that is 16 divided by pi d. When you do, you are going to get that ds, and then P is nothing but the perpendicular distance. So if you try to write this equation, the total area you can consider pi r square, because radius is nothing but 381. So total area would be pi into r square for the circular cross section, and you are going to get it as, this is square, so you're going to get it as 4.56 into 10 to the power of 5 mm square as the area. And then if you try to write the shear flows on the right side, and you can use the torsional moment formula, that is 2aq, you can use torsional moment formula, okay, because it is a cross section. So 2aq. So what we are going to do here it is, and we are going to make this 1 2, we are going to split into these panels like this 1 2 3 4 5 6, okay, and then this one, and then this one, this one, this one, this one, this one, and then this one. All this we are going to make it into 16 areas, because we got the total area and there are 16 panels. So if you divide total area by 16, you are going to get each panel area for A12, A23, which are similar. So divide by 16. So therefore, the total area here, the total area is 4.56 into 10 to the power of 5, and when you divide it by 16, you are going to get all the areas A12, A23, and so on. Okay, so I am putting this in the formula so that the total each area is equal to 28,500 mm square. So when you try to write this equation on the right side, cyclic integral of QB into PDS, it doesn't mean that minus 2AQ. So minus 2 into A12 into QB12, minus 2 A23 into QB23, minus 2 A34 QB34, and so on up to how much you are right, up to 16 one panel. So minus 2 into A16 QB16 up to here you are right. And next is nothing but the shear flow due to constant, that is constant shear flow, moment due to constant shear flow, which is 2A QS naught. Now here you are going to substitute total area. Total area you are going to substitute, which is nothing but 4.56 into 10 to the power of 5, and QS naught we will write as it is. So writing this part is important, okay. And here also you can take this minus 2 common, or you can take the 2 common, and then A12, A23, and so on, A16 So we've seen from this equation that all the areas are same. So you can take 28,500 also common. So once you take 2 and area as common, so you left with, in this equation, you left with only the shear flows. You can straight away add the shear flow, that is minus QB12, minus QB23, and so on up to 16 QB16 you can add all the shear flows. So in the diagram we got, in the tabular column we got all the shear flows, that all the shear flows you can add, and you can write the value here, and therefore you can get this as 100 into 10 to the power of 3 into 150, that is equals to 2 into 28,500, which is take common, and then all the shear flows can be added here, plus 2AQ, 2 into area of the total cell, that is 4.56 into 10 to the power of 5 into QS naught. And when you add all these shear flows, that whatever we got in the tabular column, and try to solve for QS naught, you are going to get QS naught equals to 32.8 Newton per mm. Okay, and it is acting, you got a positive one, it is acting because QS naught we considered the clockwise QS naught we considered. Okay, and then here we got minus, you're going to get minus 32.8 Newton per mm, and that you can consider it as clockwise, that we considered as clockwise, and that you can take it as plus 32.8 Newton per mm, and which you can take it as acting in anti-clockwise direction. So once you get all these things, and you can complete the shear flow distribution by adding this QS naught value to all the QB values. Okay, so for example, QB12 we have assumed it as 0. Now this one, it will become what? When you add QS naught, it will become, so Q12 that is equals to QB12 plus QS naught you have to add. So QB12 is 0, that we have assumed, plus QS naught if you add, it becomes 32.8. So Q12 you are going to get 32.8 Newton per mm. Okay, now that is drawn here. Next, similarly, if you try to add Q23 is equals to QB23 plus QS naught. Okay, so how much we got QB23? So let's try to see here. QB23 as we got minus 33.3. Okay, and so QB23 we got minus 32.3. Now this we got minus 32.8 in the clockwise sense. In the similar sense, that you can add minus 32.8. So together you are going to get minus 63.1 Newton per mm that we got. But this is in which direction? Clockwise direction. So in the, if you try to write in the anti-clockwise direction, so you can write this as 63.1 Newton per mm, and then you can write this as anti-clockwise direction. Okay, this is Q23 actual. So like that, all the shear flows are should be modified, but that is for all the QB values you have to add the existing QS naught what we got from here in this equation, minus 32.8 in the clockwise sense, or you superimpose directly. We have drawn two diagrams, right? This is what we got. For example, here if you assume you got negative, so 2, 3 you can assume to the same direction since we got negative, and now you try to superimpose that clockwise directions on this one, then all the shear flows will be added up. Okay, sometimes it may be subtracted also. So superimpose all this and add to all these shear flows, so you are going to get the actual shear flows. So the actual shear flow distribution is depicted here, and which is shown here in the diagram. So 2, 3 you got 63.1, 3, 4 86.3, and 4, 5 you get 4, 5 and 5, 6 both you are going to get similar 98.8, and 6, 7 86.3, and 7, 8 63.4, 8, 9 32.8, and 9, 10 as 0, and 10, 11 30.3, 11, 12 53.5, 12, 13 and 66, 14, 15 as 58.5, and 15, 16 as 30.3, and 16, 1 as 0, and 1, 2 as 32.8 that we have seen here. Okay, so this is how the complete shear flow distribution can be calculated for the fuselage cross section whenever it is subjected to a shear load, and which is acting at a distance of 150 mm from the centroid. Okay, now if you look at the torsion, so torsion here, earlier we have drawn the diagram. Okay, earlier we have seen the diagram that 150 mm is acting 150 mm, and in this diagram we have added. Okay, here we have considered that is 100 kilonewton is acting at a distance of 150 mm. Now it's going to create a torque about the centroid X1. So what we are going to do here it is, so a load can be converted into a torque and load, so that that 150 into 100 into 10 to the power of 3. So now it becomes the torque. So torque equals to 15 into 10 to the power of 6 Newton mm it becomes, and the load shifts to the centroid. So this how we are going to replace. So here we are going to replace like this. So 100 kilonewton acting at the center, and provided it's going to create a torque that is equals to 15 into 10 to the power of 6 Newton mm. Okay, so this is how we are load is converted into torque. So directly he is going to give a torque like this acting at the centroid. So now if you look at the torque and how we can able to solve these problems. So the shear flow distribution produced by a pure torque is therefore given by Q equals to T by 2A from the torque equation, that is T equals to 2AQ, so that the shear flow would be equals to T by 2A. Okay, and if you consider the similar one, so that I given that the load will be shifted to the centroid, that is 100 kilonewton, and it will be created a torque that is equals to 15 into 10 to the power of 6 Newton mm. Now for this particular problem, for the similar problem, and he has given a torque instead of shear load that is acting at 150 mm from the centroid. Now he is giving that shear load is acting at the centroid with a torque of 15 into 10 to the power of 6 Newton mm. So if this is the question, then slightly our procedure will modify according to the torque we can consider, and the procedure goes like this. Okay, so the first thing is the shear flow in 9.8, 9.10, 16.1 and 2.1 is equal. So what we'll consider first, 9.8, 9.10. So 9.8, 9.8, 9.10 and 16.1, 1.2. So these are equal, isn't it? The shear flows, because of the doubly symmetric in nature, the shear flow in these 4 panels becomes similar. So therefore, for the first equation, what I am writing here, it is the shear flow in 9.10 that is equals to shear flow in 9.8 that is equals to shear flow in 16.1 that is equals to shear flow in 1.2. This is the first condition I am taking. The next condition when I write, I am writing the shear flow in 8.7 that is equals to shear flow in 10.11 that is equals to the shear flow in 2.3 that is equals to the shear flow in 15.16 must be equal to this Q12 plus 30.3, the shear flow distribution what we got from the previous one, QB. Okay, so like that we have to go the procedure. So 30.3 is the shear flow that we have to add to 2.1. Okay, so where we got this 30.3, the 30.3 is the shear flow that we got from the previous shear flow analysis. Similarly, the next 4 shear flows, 4, 3, 7, 6, 11, 12, 14, 15 is equal to what we have to add, 53.5. Next 5, 4, 6, 5, 12, 13, 13.4, it is 66.0. So that we have to add for Q21. So the resultant of all these shear flows is statically equivalent to the applied shear load. So the applied shear load, we have to consider the resultant due to all these shear flows, and that must be equal to the applied shear load. So the applied shear load is 100 kilonewton. So 100 into 10 to the power of 3, and that should be equals to the resultant of all the shear flows. So we know that a shear flow, when multiplying with its length, it is converted into shear force. Okay, so therefore what I am trying to do here, it is, so I am so this is the shear flow what we got, that is 30.3 into Q21. So then I am trying to write the shear flow multiplying with its length and writing as one equation, so that I am going to get this equation as 4 into, because everywhere there are 4 shear flows. So first for 4 into, that is Q21 into, and what we have to add is 29 is nothing but the length, and then for 3.2 you have to add 32.5, and then for 4.3 you have to add 123.7, for 5.4 you have to add 145.8. that is nothing but the shear load. And from the above equation, if you try to do and converting all that equation into Q21 by using the previous expression, then we are going to get substituting everything for 3.2. For 3.2, what I am doing here, substituting, it is equals to 30.3 into Q plus Q21. For 4.3, substituting 53.5 into Q21. For 5.4, I am substituting this as 145.8 as 66 in plus Q21. So now all the shear flows will be in terms of Q21. So when you try to do this one, straight away you are going to get Q21 from here. Okay, so once you get Q21 shear flow, you can add to all the shear flows. So Q21 once you get here, you can write here straight away. So you can substitute all this, you can get all the shear flows, 16 shear flows, that is Q shear flows, all that you are going to get. Okay, so the only thing is nothing but what, here in this equation, the shear flow, that is the resultant of all these shear flows, is statically equivalent to the applied shear load. And when you try to write this equation, and for this Q21, that it will be multiplied by 29, which is nothing but the length. And if you look at the diagram here, okay, so 21 is nothing but that you have to consider, it will be its length. So like that, if you try to calculate all the lengths, and then if you try to put in the equilibrium and consider all the forces for 3, 2, 4, 3, 5, 4 along with the lengths, and if you try to substitute all these lengths, and you're going to get Q21, that is equals to 16.4 Newton per mm. And once you get this Q21 16.4, you can substitute for all the rest of the three equations, the shear flows, and you are going to get all the rest of the shear flows. So this is how problem with torque that is given, we are going to solve like this. Okay, and the shear flow distribution due to the applied torque, and is given by Q equals to T by 2A. So T is nothing but 15 into 10 power 6 divided by 2 into A, that is equals to 4.56 into 10 to the power of 5. So that you will get Q equals to 16.4, because the shear flow distribution due to the applied torque is nothing but Q equals to T by 2A. So this is the total area of the cell, and you get shear flow is nothing but 16.4. And then Q21, what we got from analysis is 16.4, and here we got 16.4, that you have to add together, so that you will get Q21 equals to 16.4 plus 16.4, that is equals to 32.8 Newton per mm. So like that, again you can add the 16.4 to all these shear flows, 3, 2, 3, 4, 3 and etc. So then you are going to get the all the shear flows. Okay, and for the last shear flow 16.1, you are going to get 16.4 minus 16.4, that is equals to 0. Okay, so this is how we try to solve the problems on shear flow distribution when they are subjected to torque, or they subjected to torque that is applied over here. Okay, so that's it from today's session, and in the next session we'll discuss about the shear flows corresponding to the wings, okay, or the stress distribution in the wing. So thank you everyone for watching.